All right, so we're going to start our notes 10.1, 10.2, 10.3, parts of a circle, arc measure, and properties of chords. So first of all, vocabulary. A circle. A circle is defined as the set of all points in a plane that are equal distant from a given point. The equal distant from the given point is the center of my circle. The center of my circle, and then all of the points around are equal distant. That's how it makes a circle. The center is the point in the circle from which the points are all equal distant, what I just said. Equidistant. Which is always in right here. And they always name a circle by the center. So when it says something like, you'll see something that looks like this and it'll say C. C is the center of the circle. And so they always name it with like a little thing that's like a bullseye and then the letter of the center of the circle. That's how they name a circle, always by its center. The radius is a segment from the center of the circle to any given point outside. So here is my center. This is a radius. This is a radius. This is a radius. It has not changed from elementary school. The radius is still half of the circle in the distance. Yes, sir?
Why did the circle get bigger?
I don't know. So you can see it better. All right. A chord. A lot of this you already are kind of aware of. A chord is a segment whose end points are on the circle. Excuse me?
Are those lowercase r's?
Yes, because they're radius.
Why aren't they?
Because they're a radius. That's how it's always done, is lowercase r. A chord is a segment, as you said, the end points on the circle. It does not go through the center. A chord just takes 2 points on the outside and connects them. If it goes through the center, then it becomes a diameter. A diameter is a chord that goes through the center of the circle. So if I have AB, it goes through my center, it then becomes a diameter. And as we know, a diameter is twice my radius. So a diameter is just a chord that goes to the center, and a chord just connects 2 pieces of the circle on the outside. Okay, next we have a secant. A secant is a line that intersects the circle in 2 points. It's always a line that's basically going through my circle. So here, if I just have a line going through here, that's a secant. It's going to connect in 2 places. So it's basically a line that goes through a circle. Yes?
What's the difference between that and a chord?
It goes on forever. It's a line. The chord is a segment. The chord is the segment from the 2 sides. Good question. This is a line that goes on forever. The tangent is a line in the plane. I don't know why they put plane there. In a plane of a circle that connects in only 1 point. A tangent's always on the outside because it only hits 1 point. So a tangent will always be like this, just hitting a 1 point. Because as you know, a circle, as it makes its roundedness, there's only 1 point that's actually sitting out there that it's going to touch. It looks to us visually like it touches more than 1 point, but it only touches 1 point. So a tangent's always outside, a secant's going to cut through. Okay? Tangent and secants and chords. Mm-hmm. No, it's not that same tangent. That's a tangent for a trigonometric function. This tangent is just called a tangent because he's going to actually make a 90-degree cut to the circle, which then you could use all that other mess, but it's not the same tangent. Same word, different thing. All right, so with just this set of vocabulary, we have a couple things going on. So we have theorem 10.1, and this is where the tangent comes into play. It says, in a plane, a line is tangent to the circle if and only if the line is perpendicular to the radius at the endpoints. Which means that here I have a tangent. He's perpendicular to my radius. He's always going to make a 90-degree line, 90-degree angle, always. Because he's always going to be perpendicular to my radius. With my tangent as well. tangent segments from a common external point are congruent. This is important. It's saying that R is a tangent, T is a tangent. I have this external point S. The two pieces making the segments to the external point are congruent to each other. And that's important. This unit has a ton of congruency that occurs for different things. That's why I gave you that quick reference chart. You're going to see that there's a ton of different things that happen depending on who's going where, when, why, or with a circle. That's why people think circles are difficult, but as long as you remember who's congruent to who, you're fine. It's more mathematical, this unit, than last unit was more thoughts. This is more mathematical. All right, finishing up our vocabulary. Central angle. A central angle is an angle who is formed from whose vertex is the center of the circle. That means I have my center here, C, that we've talked about. The central angle is formed off the center of the circle. That's called our central angle. Why? He's formed from the center. Other angles are not necessarily formed. We find out later angles can be formed in different places. The minor arc. The minor arc is the part of the circle that is less than 180 degrees. Okay, we're talking about measuring arcs. When you're talking about measuring an arc, there's going to be a minor arc and a major arc. The minor arc is less than, no, you're going to have a semicircle, but a minor arc is less than 180. So when I'm measuring my arc, the arc is the distance here from A to B. It's the outside. And when you write it, it'll say arc AB. It looks like part of the circle you're covering. It's not a straight line, it's an arc. It's a curved line above it. So its measure, because you're going to have to find the measure of them, its measure is from 0 to 180. Then we talk about a major arc. With a major arc, its measure is 180 to 360. So it's between 180 and 360, which means that if here is C, you're always going to, not always, but usually you're going to have 3 points, so you know. You might still have your A and your B, but then you might have like, I'm going to make it bigger than that, sorry. Like D over here, where I might say arc BDA. This tells you the direction to measure it in. It's saying starting at B, I'm going to cross D, and I'm going to go to A. It's going to be over 180 degrees because it's the major arc. Usually, they are 3 letters. Usually. I can't say it's consistent with that rule, but usually it's 3 letters. Or it'll have to tell you the major arc. Yes, sir?
Couldn't AB be a major arc if it went?
AB cannot be the way I've drawn it.
It would be ADB.
It would have to be ADB, so you know to go that way and not make it the short way. It would have to tell you, so you would know not to measure from here to here. It would have to tell you that the major arc AB, so you know to go the other direction, or it would name it by the 3 points. When you look it up, because we had some discrepancy with this last year, when I looked it up online, it always named it by 3 points. I can't say your textbook's consistent with that. But it will say the major arc. It'll tell you that you have to go the other direction. Because otherwise you wouldn't know if you're looking for you'd have to know you're looking for the bigger angle, or it'd have to tell you find the major arc. Something to let you know it's the bigger route. A semicircle is an arc with endpoints. The endpoints, or the diameter, sorry, I had to look at the vocabulary word. The arc with endpoints that are the diameter. When a semicircle, when you know, your endpoints are your diameter because it's half of your circle. It's like doing a 180, it's half of a circle. Same idea here, it's a semicircle. You've seen semicircles for a long time. When it asks you the degree and it gives you AB and it goes from diameter, it goes the diameter distance, you know it's always 180 degrees because you're going to have to find arc measures, which we're getting to right now. The measure of a minor arc. The measure of the minor arc is just the measure of its central angle. Because the minor arc, when you have your circle, the distance right here, whatever degree I have here, so say my central angle is 60 degrees, it's a little tiny 60 in there. If that is 60 degrees, then the measure of arc AB is the same measure, 60 degrees. So whatever measure that angle is there, my minor arc is the same as my central angle. which brings us to the major arc. How many degrees are in a circle? 360. If you skateboard, you do a 360, or a snowboard, you do a 360. There's 360 degrees in a circle, or if you remember the rotations, you go around 360 degrees. The measure of the major arc is the difference between 360, which is the total degrees in the circle, and the measure of the related minor arc, which makes sense. If I only have 360 degrees here, just drawing the same picture I have above, and this is 60 degrees here, then what's got to be left over? It's got to be 360 minus my 60, so my major arc would be 300 degrees. It's always the leftovers from the minor arc, because your central angle will not, central angle, anyway, is usually less than 180.
And this is going 80 degrees.
This is going the one we had before. That way.
Do you have to have 3?
How would you know if you don't have 3? Unless it said the major arc. That's the only thing. You do have to have 3. Your book does not always have 3, but I will tell you, as you get into higher math, it says on like I looked on YouTube, it'll say it always has 3 points. But I can't say that's consistent with anything we do. It would have to tell you the minor, it'd have to tell you the major arc. It would have to tell you. You'd have to know to go that way instead of the short distance for 60. You'd have to know something. So measuring arcs, this blurb is really just everything I've already told you and shown you, is that here it just says it has a little M in front of it, just like your angle measure. It's got a little tiny M in front of the arc. And so the measure of the entire circle, as we said, was 360 degrees. This should kind of always be in front of this. The measure of the major arc is the difference between 360 and the related minor arc, which we already talked about. And the measure of a semicircle is 180 degrees. So it's everything from above. Nothing fancy. And last little bit of vocabulary, and then we have some practice, which is easy. All right, so a congruent circle. A congruent circle is 2 circles are congruent if they have the same radius. So to be a congruent circle, your radius has to be the same, which means it can be a circle inside of a circle, or if you have a circle next to it, their radius is going to be the same. We'll see some examples of that in a second. But a congruent arc has 2 criteria. One, it has to be a congruent circle, which means their radius is the same, and their arc measure is the same. So to be a congruent arc, it says 2 arcs are congruent if they have the same measure and their arcs are the same circle or congruent circles. And we'll see examples of what they're talking about. Because there are some circles that are drawn on top of each other, and although their arc measure is the same, their radius is not. So therefore, it's not. They're not congruent arcs, even though their measure might be the same. They've got to be a congruent circle as well. Yes, Paige. Got it? Okay. Okay, the arc addition rule. The arc addition rule is the same as the segment addition rule, same as the angle addition rule. It just says if I have 2 arc measures, I can add them together. That's all it says. So it says the measure of an arc formed by 2 adjacent arcs, and the sum is the measure of the 2 arcs. So here, the measure of arc ABC is the measure of arc AB plus AC. AB, wait, sorry, plus BC, sorry. Yeah, BC. I was looking at it backwards, plus BC. So go AB plus BC. And it does have that little arcy thing over it. All right, now we're just going to talk about some congruents that are formed, and then we're going to start some practice. So on 10.3, 10.3 says that in the same circle that 2 chords are going to be congruent and 2 minor arcs are going to be, in the same circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So it's saying here that if this chord is congruent to this chord, and it tells you right here that they're congruent or they'd have the same measure listed by them, then the arc formed here and the arc formed here are congruent. So if AB is congruent to CD, if and only if AB is congruent to CD. So the 2 chords have to be congruent. Those are segments. Then the 2 arcs are congruent, which makes sense because it's the distance from here to here. This distance, this measure has to be the same. So to find its arc length, It's arc measure, sorry, not its arc length, because that's separate. It's arc measure, then you might only be given, like, you might have here, I'm going to say 125 degrees. Then this one right here is 125 degrees. So it's going to ask you to find an arc measure, and you might have to look at the other one to see it because of the congruence. Yes, ma'am?
How would you show that the arcs are congruent? Would you put like a line through it?
No, it's still the congruent signal. It's just AB is congruent to CD. It's just a congruent symbol between the two arcs. I don't know. Somebody else asked that last year, and when you're talking segments, you use the dashes. So I don't know. However you want to represent it, there's no symbol for that. Unless you want to put the congruent symbol on it yourself, you can do that. It's whatever makes sense to you, but there's no, like, this is how you show an arc is congruent. Like with segment dashes and angled things. Just be careful, because if those are congruent, if you want to use like extra slashes, or somebody last year did wavy slashes instead, but it's not a formal thing. All right, theorem 10.4. It says, if one chord is a perpendicular bisector of another chord, then the first chord is the diameter. So that means, it says here, if QS is a perpendicular bisector of TR, who is the first one I mentioned? So who's my diameter? QS. So then QS is the diameter of the circle. Right, and because that means QS would go through the center. So the other one bisected it, is a perpendicular bisector. The first one listed is the diameter. So it would help you know who's the diameter of the circle. That's what the theorem says. The first one listed needs to be the diameter. That way it doesn't tell you it goes through the center, but because he was listed first, our theorem tells us it went through the center. Theorem 10.5 says, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So it's basically saying that now that I know that here in this one, EG is my, EG is bisected by FD. So now that I know that, then it bisects it at a 90-degree angle, because it says before that it's perpendicular. So now you know that there's a perpendicular symbol here. That's all it means. So it says if EG is the diameter and they're perpendicular, then we have HD is congruent to HF. So now, because of that, then we know that, DG is congruent to FG. So because this crosses here and bisects it, which it should already kind of tell you because it bisected it, this piece is congruent to this piece. So we know that HF is congruent to HD. Oh, and, the arcs are congruent, That's what I was missing. The arcs here are also congruent, because if the pieces are congruent, then my arcs have to be congruent. I knew I was missing something, sorry. So I'll say that again because I kind of messed it up when I said it the first time. So if EG is the diameter, it bisects it. The two pieces, because it bisects, are congruent. Because the two pieces are congruent, the arcs that are formed by those two pieces are also congruent. That sounds much easier. And then the last theorem plays on the same bit of stuff. It says, in the same circle, or in a congruent circle, two chords are congruent if and only if they are equidistant from the center. So now we know that CD and AB earlier, if they were congruent, then their arcs are congruent. It's saying that now they can be congruent if they're the same distance. So if here EF is congruent to EG, then we know automatically that AB has to be congruent to CD. Got that? Can you say it again, or is that, we understand that? That if these two pieces here are congruent, then these two pieces here are automatically congruent. Because they have to be the same distance. Because the circle's round and congruent, they're forced to be congruent as well. So then you'd have AB congruent to CD, which then makes arc AB congruent to arc CD. So it's just a lot of little things with my circles. Okay, a lot of little things. So let's go and look at some practice on them, because they're not as bad as they appear. So first piece is mostly vocabulary. It says, tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. And that's how you'll always see the circle C. It's always named by its center. The center names the circle. So looking at BC. So BC is right here. What is BC in relationship to my circle? It's a radius. It's a radius because it is from the center to the side. It's a radius. Okay, EA is what? It's a secant. Why is it a secant? It's a line that crosses my circle twice. Remember, a secant cuts my circle twice. So because it cuts the circle twice, it is considered a secant. What about line DE? It's tangent because it only cuts my circle once, so it's considered a tangent. And as I said, tangents are always on the outside. I don't know. All right, so in the diagram, we can play it back. In the diagram, find the given lengths. The hardest part about the diagram and finding the given lengths is just making sure you know who's the center of which circle. Because the center has to be what from its sides? Equidistant or equal. So if I'm looking for the distance of my radius A, so if here is my radius of circle A, I'm going to be using my small circle, so it's only 2 units because there's no units on it. But then my diameter is the whole distance across is 4. You can count 4 blocks. The radius of B. All right, well, here is B, so we know it's got to be the big circle because it has to be in the center. So the radius would be 1, 2, 3, 4. And then my diameter would be 8. This next question is a very good question. It talks about how many tangents can be drawn from this picture. And this is why I chose the textbook over the workbook, because this is not in there, but it is on your quiz. So it's going to say how many tangents can you draw from here. You need to know the vocabulary word tangent means how many times is it going to touch my circle? Once. So looking at my first one here, how many different ones can I draw? Well, I can draw one on this side to touch each one once. I can draw one on this side to touch each circle once. And because my circles are right here, I can actually draw it in the middle because they're just touching literally by 1 point. So it'll touch 1 point on each side, so I have 3 tangents.
How do we know that it's just touching?
Because it doesn't overlap like this. If it's going to overlap, it'll look obviously to overlap. Otherwise, if they're just butted up next to each other, it's like 1 point that would actually from each one be further, and they would just barely be touching, like barely touch. So we're not going to assume. We know it's going to happen, although our picture doesn't always represent that. The second one would only be 2 because it can't be the middle because obviously the 2 middle circles overlap like those Olympic symbols. So it would just be these 2 this way, so there's only 2. What about my last one? 1. And you'll have some of these in your homework tonight to do as well. It's just going to say how many tangents can be drawn. It's understanding that the vocabulary word tangent means it can only touch my circle once. So it's always going to have to be outside of my circle. How many secants could be drawn? A lot. Because secants got to cut twice in my circle. Yes?
Tangents like not intersect. Why couldn't you draw them on like the top of the circle?
Because it says it has to hit both circles. And it's a straight line. It says how many common tangents. So it'd have to hit both circles. That's why you can't do it on the top. Number 4 is a great question. And number 5, definitely on quiz, definitely on test. What are you doing? It's basically saying that in this diagram, RS,
You did say 3 was on a test.
yeah, quiz. It's Pythagorean theorem. It says in this diagram, how do we know, so we know that RS is the center. How do we know that ST is a tangent? Well, what is the tangent form? What kind of angle? A right angle. That was an SAT question, by the way. A right angle. So if it's got a right angle here, means it's tangent to the circle because it's going to be right where the line hits the circle. So how am I going to prove it's a right triangle? Pythagorean theorem. What did I tell you? Your Pythagorean theorem and your trig functions, anytime you have a right angle happening, they can pop up. No one's going to say, hey, I got a right angle. Hey, remember Mr. Pythagorean theorem? They're just going to say, hey, how is it formed? And you just need to know that the Pythagorean theorem is the most used thing, I think, in geometry. So here, to use Pythagorean theorem would be my legs squared. So my legs would be RS and ST. So 24 squared plus 10 squared equals 26 squared. So if it is true on both sides, like our unit before last, then it is a right triangle. So is it a right triangle?
Yes.
Because what do you get when you do the 2 sides? 676 equals 676. So yes, it is a right triangle. Because to be tangent to the circle, it has to form a right triangle. And it may just tell you in the directions. RS is tangent to the circle. So that way you know that if it's tangent, then you can use it. So then how is number 5 different?
You have to find the missing side.
You're going to have to find R. And to find R, it already tells you that B is a point of tangency. So that means I have a right angle here. Means I'm going to have to do a little foiling when I go do stuff, because R squared plus 77 squared equals what? What is the distance of AC? 49 plus R is squared. And if you recall back to our little algebra days, that means 49 plus R, 49 plus R, FOIL, and add together. You can do the box. I just didn't do the box last year with my students because it's in the middle of the thing. So yes, you can do the box. Box does the same thing. What is 77 squared? If you write it the right way, it works. 5929 equals what? I wrote it backwards before. 2401, yikes, 2401 plus 98R plus R squared. Now, at this point, I have to think about what's going to happen. Do I have to factor? If I have to factor, my whole problem is going to have to equal 0. But because I have an R squared on one side and I have an R squared on the other side, when I bring them together, what do? They cancel out. So therefore, I know I'm not going to have to bring everybody to one side because I have an equal R on both sides. They're actually going to cancel out when I go to subtract them off. So because I have the same thing, so I'm not going to have to worry about factoring. So here, I just go ahead and bring my number over by subtracting 2401 from the side. Divide by 98. So my radius equals 36, and it didn't give me a unit, so 36 is fine. Or you can put 36 units either way. So think ahead before you start doing too much work that if my R squareds are different, I may have to factor. But because my R squareds are the same, they're going to cancel each other out when you subtract them off. So I'm just left with regular old R. And a lot of times, because of the way the R squareds work, that's what's going to happen. A lot of times it's going to be like this, not actually factoring. Next theorem of fun. QR is tangent at circle C and at R, and QS is tangent at circle C at S. Find the value of X. What do we know from our theorem? We know that from our theorem, and it's actually theorem 10.2, just recalling it for those who are not here, says that if you have an external point, the two pieces are congruent as long as they're both tangent. So 32 equals 3x plus 5. Now I just solve for x. So x equals 9. Sad looking 9, but 9. It's just knowing the two pieces are congruent. Okay, on number 7. Number 7 says, find the measure of each arc of circle C where DF is our diameter. So it tells us we're trying to find the measure of DE. That means I'm going to go straight from D to E. It's the same measure, that's a minor arc, so it's the same measure as my central angle, which is 117 degrees. Yes, it's an angle measure. It's always degrees. Even though it's outside, it's still a degree. It says, what is the measure of DFE? So DFE means I'm going to take the longer route, DF and then E. So how am I going to do this major arc? 360 minus 117 gives me 243 degrees. Because if it's a major arc, it's the 360 minus my minor arc. Yes, sir?
Why is it measured in degrees?
Because it's an arc measure is the same thing as an angle measure. They're all degrees.
And then the next one is 180 minus
Well, it's DEF. What is DEF?
180.
It's half the circle. It's a semicircle, so it's just 180. That's okay. It's just a semicircle.
What I meant, but
Say what you mean, you just say it. It's a semicircle. It's the diameter, so it's 180 degrees. Which, when you're starting to find some arc measures in your book tonight, because we're going to do some workbook stuff, just not tonight because it's missing some things that I want you to be able to do, is when you start looking at things, note that sometimes they might ask you for EF. And because it's a semicircle, it's 180, you can just subtract 117 from 180 to get the missing things. So always look for your semicircle because it'll help you off your central angle to find missing measures. Always look for what you know. Okay, on number 8. On number 8, it says, you're joining a new bank and you're going to divide your money several ways, as shown in the circle graph to the right. Find the indicated arc measure. So what's the measure of BD? So BD is going to come this way around here. So how am I going to find BD?
Because it's not a major arc.
Because it's not a major arc, because I got to go straight from B to D. And the only reason I know, and this is what somebody asked me, was it last year or the year before, I can't remember, is if it doesn't have 3 points, I always go with the minor arc first. Because that's what it says. So this is what it says. It doesn't ever say that in your textbook anywhere. But if it only has the 2 points, you should go the shortest distance there. Goes directly from B to D, the shortest distance, so it makes it the minor arc. Because here is going to tell you to take C as a side part, to go the route of C. So on A, we're going from B to D. So what's going to be the measure of arc BD? It's going to be the 55 degrees plus the 105 degrees. So it's going to be 160 degrees. How did we come up with that? That's the theorem that says you can add them together. I don't remember the number, but it says that we can add the measure of arc BA. It's a postulate. It's probably a postulate then with the segment addition postulate. Yeah, they're postulates for the others as well. Plus the measure of AD puts them together. You just put them together. So now the measure of BCD. So it's telling me I have to go this way around here. So what's the measure of BCD? You can either A, add the two together, or 360 minus my minor arc. So 360 minus 160 makes it 200. Would it have been wrong to measure BC plus CD? No. You can still add the two together. It's not a problem. Okay, the next piece talks about our congruent circles. To tell whether the arcs are congruent. For an arc to be congruent, it has to have two things. The circle has to have the same radii. I don't know if it's isn't it radii? I. And the circle, then the arc has to have the same measure. So same arc measure. Shh. So same arc measure. So when we are doing number 9, we need to look first that tell whether the given arcs are congruent. So first, do they have the same radii in this circle? Are the circles congruent? Yes, because first of all, it's the same circle, so it has to be congruent. So the circle is congruent. And then my arcs have to be congruent. So here, for BC, what's its arc measure? So the measure of BC is 75. And then what's the measure of DE? So are the arcs congruent? Yes. On B, well, the first thing is they have to be a congruent circle. So are the circles congruent? No, because their radii is not the same. For the first circle here, this distance right here is obviously shorter because it's the inside circle than the distance for the bigger circle. So the circles are not congruent. Because your circles are not congruent, therefore, it doesn't matter if your arc measure is the same, your arcs can't be congruent. Does that make sense? Because what's the arc measure for both of them? 80. It's 60 for both of them, or is it 80? 80? So it's 80 for both of them, but because their circles are congruent, the arcs can't be congruent. So it's no. Has to be both things. All right, and then C. Are my circles congruent? Yes, it tells me right here the radius are the same, so my circles are congruent. Are my arcs congruent? My arcs are both 90 degrees, so therefore, yes, they are congruent arcs. All right, the last two examples, because we can't do number 11. We haven't done constructions yet. You have to be able to do constructions, and we haven't gone over those yet. So, on number 10, in the diagram,
In the middle, on the seam.
in the diagram for number 10, circle A is congruent to circle D. That means they have the same radius. It says BC is congruent to EF. That means the chords are the same. It says the measure of arc EF is 125. So what's the measure of arc BC? 125. Because of, I didn't write the theorem number down. The theorem says that if the chords are congruent, then the arcs are congruent. So the measure of arc BC is 125 degrees. And the theorem, I believe, is, which theorem? Theorem, it's the backwards of the other one. So yeah, the theorem, it's theorem 10.3 backwards. So it's 10.3. All right, and then number 11, he's got to stand somewhere in the middle. We will actually do this later. You do it by doing the perpendicular bisector, and I got to make sure it's not in the homework. You got to do the I think I took it out. The perpendicular bisector of the one, the perpendicular bisector of the other, and then where they cross is gonna actually be the point of. It's going to be some kind of in the middle, like right here. We will actually do the construction later for this. There's no sense of doing the construction now, gentlemen, because we'll need it for the SOL test, so we'll do the construction later. Do it after spring break. We'll do all of our constructions. It's one of the things that got pushed away with snow days, so we'll go back to do that. So you can't do number 11, and I'll double check it's not one of the homework problems. All right, on number 12, it says use the diagram in circle E to find the length of BD. Tell what theorem you used. All right, so what is it telling us here? What do we know? Use the diagram in circle E to find the length of BD. So what do you know?
12.
What do you know?
Theorem 10.5.
What does theorem 10.5 tell us?
If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in its arc.
There you go. It says that, I'll read it out again louder so it's louder for the thing. It says that, and if the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in its arc. So therefore, it's perpendicular right here. It bisects, so these two pieces are the same. DF is 6, which means that DF equals 6, which means BF has to equal 6. So therefore, the total distance of BD is the two added together, which is 12. And that's the theorem 10.5. Excuse me, yes.
I thought the middle was always C.
No, the center of this circle, it says it's circle E. It doesn't say it's circle C. It says it's circle E. So E is the center. No. I said it's always by a circle symbol to tell you who your center is. The circle is not always C because C might not even be one of the variables in the circle.
Rewatch this video.
All right, on number 13, gentlemen. Last time I will stop us talking while I'm recording. In the diagram F, AB is congruent to CD, which is 12. Find EF. So if the two chords are congruent, what do you know about the two pieces that are perpendicular to the chords? They're both congruent. It falls back to our theorem, was one of the last ones we did. Theorem 10.6 says that if the two pieces are congruent, then these two pieces are congruent. So that makes perfect sense, right? These pieces are congruent, and these pieces are congruent. It says on 10.6 that in the same circle or in a congruent circle, two chords are congruent if and only if they are equal distance from the center. So if these two are equal distant, which means they have the same measure, which means FE has to be equal to FG, then the two chords are then congruent. So what is X? So X equals 2. It's knowing the theorems and knowing who's congruent to who to make it happen.